So today's video is going to be on section 1.5 from our text entitled Constructions of Vector Spaces. Now I know in last class we didn't quite get through as much about dual spaces as we would have liked, but I kind of want to do most of that in person. So when we come back next Wednesday, I'll probably cover a little bit more about dual spaces before we move on to section 2.1. But for now, we can talk about constructions of vector spaces without really needing to know any more about dual spaces. We'll start off with a few definitions, so if you've read the book, you might be able to skip some of this because you would have already seen them, unless you had a question about a particular definition. I've kind of cherry-picked a few that I thought were important. The first one is what it means to add two subspaces together. So if you start with two subspaces of a vector space U, adding them together is basically the collection of all vectors that can be written as the sum of a vector in V and a vector in W. This leads us to the idea of what we mean by a direct sum. So if a vector space U is a direct sum of subspaces V and W, then you actually require two things. First, that U is equal to V plus W, but also that V and W intersect as trivially as possible. Since they're subspaces, they both have to have the zero vector, and so that's the only thing we allow to be in the intersection. In this case, we'd call W the linear complement of V and vice versa. So V is the linear complement of W inside of U. It also means, and this is something I want you to think about whether or not you can prove it, that every element of U can be written uniquely as the sum of an element from V and an element from W. It turns out that this follows from the fact that V intersect W is empty. If it were possible to write an element of U in two different ways, as a sum of an element from V and an element from W, then you could be able to show that there's something else in the intersection besides zero. See if you can work that out for yourself, and if you want, you can even pause the video now and try to prove that yourself. If you can't figure it out and would like to know, we can talk about it during my office hours when I return from my trip. Now, what's interesting about the direct sum is what happens to the vector space structure of U when we break it down a little bit into what's behaving with V and W. So if you take two elements, U1 and U2 and U, and an element A from the field that U is over, both of those U's can be written as a sum of an element in V and an element in W. If I add those two elements together, those two vectors together, what turns out is that I can add the V components, the pieces from V together, and the pieces from W together, and organize it like that. I can rearrange it because of the commutative property of addition. Similarly, if I had A times U1, this would actually distribute, and I'd get an A times the V component plus an A times the W component. If you look, though, this mirrors exactly the vector space structure of the Cartesian product between V and W, which we'll call U bar, where I have ordered pairs of vectors where V is in the first slot and W is in the second. If you add those vectors together, those types of things together, you'd end up adding them component-wise. So you'd add the V's together and the W pieces together. Similarly, if you multiplied by a constant multiple, it'd hit both pieces, which is exactly what's happening up top. Okay. And so the vector space structure for the direct sum turns out to be almost identical to the vector space structure of the Cartesian product between V and W. The next thing you might ask is, well, can we do a direct sum of more than two subspaces? And it is, in fact, possible to do. And the definition is that U is the direct sum of V1 through Vk if no matter what element of U you pick, if that can be written uniquely as a sum of vectors where you get one from each of the different pieces in the sum. This actually turns out to be equivalent to saying that you can always write U as a sum of those things, and that an appropriate intersection rule is true for these guys here. But it's a little bit more complicated, so I'll refer you to the book to see that definition there, but this is sufficient for our purposes today. Now let's take a look at some theorems. One interesting theorem is this dimensionality count. If V and W are subspaces of U, and you look at the dimension of V plus W, you might expect that you'd get the dimension of V plus the dimension of W. The problem is that both v and w account for their intersection at the same time. And so the intersection is both a part of the dimensions of v and also a part of the dimensions of w, which means that if we were to add those two dimensions together, we've overcounted the intersection one more time than we should have. We counted it twice and only wanted to count it once. So to get to the right answer, we have to subtract that double count off. And that's where the formula kind of comes from. If you want, try to make that, you can pause here and try to make that into a formal proof too. And basically what you want to do is write down a basis for both v and w that's compatible with the intersection. So maybe start out with a basis for the intersection and complete that to a basis of v and a basis for w and see what happens if you add them together. What is really neat though is that if the intersection is equal to just the zero subspace, then its dimension is zero, which means this term here is toast. That's equal to zero in the case of a direct sum. So the dimension of a direct sum between v and w is in fact the sum of the dimensions. All right, now we're going to move on to two different exercises. That's pretty much all I wanted to say as far as definitions and theorems from this section. There are a few more, so I strongly recommend that you read this section if you haven't already. But now let's move into some examples and see what we can do from there. So the first example here is we want to show that the intersection of lower triangular matrices and upper triangular matrices ought to be the diagonal. Now if you think about this for a minute, it should be pretty clear that this statement is true, but let's actually go through and write everything down so we can see all the individual pieces. First, take an element that's an f in n and suppose that it's in the intersection. What we're going to do, basically, to describe the plan is, in order to show this set equality, we're going to show that this guy is contained in this one and vice versa. So to show the first subset equation this way, or subset equation, we're going to start with an element here and show that it must be in here. And remember, we want to do everything sort of from the definition. So let's call up the definition of the lower triangular and upper triangular. So if A is in this intersection, it must be in each piece individually. So we get the following. Since A is in the lower triangular matrices, by the definition, that means that Aij is equal to 0 when I is less than j. But because A is also in the upper triangular, that tells us that Aij is 0 when I is greater than j. So therefore, Aij is equal to 0 when I is either less than or greater than j, which is the same thing as saying that Aij is equal to 0 when I is not equal to j. And of course, that's exactly what it means to be in the diagonal matrices. So therefore, the intersection of lower triangular and upper triangulars is a subset of diagonals. It's a little bit easier to go the other way. If you start with a diagonal, this of course tells you that Aij is equal to 0 when I is not j, and hence in both cases when I is less than j and I is greater than j, which of course means that tells you that A is in the lower triangular and upper triangular matrices respectively. Since A is in both sets, it must be of course in the intersection. Wow, that was a bit of a typo. Get rid of one of these sum ends. You only need this piece right here. And hence you have this subset formula here. Which of course means that since we have containment both ways, we actually have set equality as desired. So that proof shouldn't have been too bad. It wouldn't be a bad idea to try to do this on your own. The reason why I wanted to present it in class too is that one of the homework problems asked you to compute something about the dimension of some of these sets, and this happens to be a sort of lemma to that problem there in the homework. All right, let's do a more challenging example now. Let's let x be the vector space of continuous functions on the closed interval a to b, where a is strictly less than b. And let's let y be the collection of all functions in that x such that the integral over a and b is 0. If we allow r to coincide with the set of all constant functions, then it turns out that x is actually a direct sum of r plus this set y. So all continuous functions of a and b are a direct sum of constant functions plus functions who integrate to 0. That's kind of an interesting idea because a lot of those functions don't integrate to 0. So it's curious that, that we end up getting a sort of one-dimensional object And this takes care of all the other dimensions of continuous functions. Let's see how it works. So as a proof, we need to show that every element in X can be written as a sum of vectors in R and Y. That would show first that X is equal to the sum of those two. Then to show that it's a direct sum, we'd have to also show that the constant functions R intersect the functions in Y, the set Y would be equal only to the 0 set. So let's first show the sum part. So let's let G be in X be a continuous function. It turns out that, of course, if you remember from Calc 1, that there's a G average value in R such that G average is equal to 1 over B minus A times the integral from A to B of G of X dx. Recall that, note too, that G average is just a real number, right? Well, this means, of course, if I multiply by B minus A, that G average times B minus A, which is still a real number, equals the integral from A to B of G of X dx. I can then subtract that to the other side of the equation and absorb it into the integral, because G average times B minus A is just the integral from A to B of G average, and I end up with this integral right here equaling 0. What does that tell you about this function here if it integrates from A to B to 0? Well, that tells you that G of X minus G average has to be in Y, because those are the functions that integrate to 0. But of course, G average is in R, and so we can write G of X as the sum of these two things. The G averages cancel, and I just get G of X. This, of course, tells me that since G of X is arbitrary, I can write any element of X as a sum of an element from R and an element of Y, which is exactly the statement that X is equal to R plus Y. Sorry, that means that X is equal to the sum of R and Y. Now the next part we need to show is that R and Y have a trivial intersection, meaning that they only intersect in the 0 vector. To do this, we're going to take an element that's in both R and Y. So for example, let's take a constant value, one that's in R, who that integrates to 0, and see what happens. So that means that if we get this integral here is equal to 0, we can solve that, and it shows that C times B minus A equals 0. Now we know from the hypothesis that A is strictly less than B, and so this B minus A part is non-zero. So the only way for this product to equal 0 then is if and only if C is equal to 0 to begin with. So the only possible way to get a constant function that integrates to 0 is if the constant function was 0 to begin with, and hence the intersection between the constant functions and the functions that integrate to 0 is in fact only the 0 function. Well, now we've shown that both X is equal to R plus Y and that the intersection is 0. This, of course, is precisely the definition of the direct sum of R and Y. That's pretty much all I needed to say about constructions of different vector spaces. There's probably a ton more examples that we could do, and certainly some that I've assigned in the homework. Some of them deal with handling the definition this way of a direct sum. Some also talk about how to use different dimension arguments to figure out the size of various vector spaces. So you can use pretty much similar techniques to what we've done here, and maybe a few others. So I encourage you to try these examples on your own, and maybe move on and try some of the homework problems now too. You should have everything you need in order to complete the homework for homework that has section 1.5 on it, and we'll talk a little bit more about dual spaces on Wednesday. Remember, we don't have class on Monday, and if you have any questions, please send me an email. Otherwise, have a great weekend.